Hey, if you're taking organic chemistry this summer, don't go anywhere. We got some more predict the product. So this is a little more, I don't want to say it's a complex one, but it's more than just a one-off reaction. This I posted, I think, 2 days ago, and we start with bromopropane right here. Yeah, methyl and propyl. We react it with magnesium and ether, then with acetone, then finish it off with just some generic acid H2O plus. So which one of these is it gonna be? If you want, pause the video right now, work this through on your own, and come back. If not, let's work through the mechanism. We're going to work through this mechanism. And if you haven't already realized, this is what's known as a Grignard reaction. A very popular named reaction. It's really good at what it does. But first, we have to make that Grignard reagent. So we have the magnesium here. It's stirring in ether. And what actually happens is the electrons from this bond go here, and then one pops itself down there. And then what we get is we get a quick radical there. And then we have this Mg plus Br minus. That's a terrible BR. How I gotta fix that? That because they formed a bond, and then we have one more dot, and then they go, all right, let's be friends here, and then sorry, my errors are kind of garbage. And then we form what's called the Grignard reagent. This is this right here, MgBr. Now remember that magnesium is actually what is bound to this carbon right here. It's the magnesium, not the bromide. It's the other way around. Don't mess it up. This is a or metallo-organic um, species. And this right here is known as our Grignard reagent. And this is what's going to be reacting in the Grignard mechanism. So I'm going to get to a fresh page. But before I do that, remember to like and follow this video and send it to your friend that's taking organic chemistry. Now that we have our Grignard reagent, remember this is a plus, this is a minus. So this carbon, this one right here, actually has a partial negative on it. So it's like a lowercase delta. Minus is like a lowercase delta positive. So because of that, this carbon doesn't really like holding that negative charge. So it's pretty nucleophilic. It's looking to offload that now. And that's why Grignards are so reactive. And you can kill them with water. So be careful putting it near water. And acid will kill it as well. Water is strong enough acid for that. But so we have acetone. So here's what we do. We'll draw on our acetone here. So here's our acetone. And so now if you remember anything about nucleophilic attack, this carbon right here is pretty primed for that because we're pulling electron density this way. And this carbon has electron density that it wants to offload. So what it's going to do is we're going to take this bond, it's going to push itself right up there. And then we're going to push these electrons up onto here. And what's going to happen, and this gets a little hand wavy here, but we form an intermediate that looks like this. Oh, and then Mg. So this was an O minus. This is an O minus, and then it converts to. Oop, I'm sorry, I'm missing two carbons. And then we come in with our H3O plus, H2O. But I'm not going to put that there. It's going to get cut off. We come in with our H2O, H, H plus, and grabs that, leading to our final product of. Oh, that's terrible. Oh. This tertiary alcohol right here. So this is our final Grignard product. So we worked through that and we showed that this makes a Grignard reagent, and then we react it with acetone and have a Grignard reaction, and then you work it up with H3O plus, just generic acidic workup. And we get this tertiary alcohol right here. I guess what that would be, what, 1, 2, 3, 4, all, I guess, and then go this way. It would be 1,1 dimethyl butanol is what it would be. Remember, Grignards react with ketones to form tertiary alcohols. Okay, guys, good luck.